Well, welcome to part B, the second part of our three-part video series. And in this one, we're going to be dealing with three tanks where one flows consecutively into the next and deriving the differential equations for each of the tanks and the flows entering and leaving each. And then seeing what happens if we increase the initial flow into the first tank by 20% and model and assess any differences with that and what that looks like over time. And so we're going to go ahead and use the same parameters as we did in the first video. Another thing is that each of the tanks, they're the same height, they have the same cross-sectional area, the flows are the same for each of the tanks, and the height levels are the same for each of the tanks at initial steady state. And so let's go ahead and start by drawing this out here. So we have our tank, our first tank with our Q in, and then we have that flowing into our second tank. It'll look hopefully roughly close to the same size. That is going from Q1, tank 1, into tank 2. And then we have our third tank. And that is tank 2 going into tank 3 and Q3 leaving the system overall. So they all have the same cross-sectional area at the top, at the bottom, where they're draining out. Well, I should be showing the flows at the bottom here. If we want to do it that way. So the size at the bottom is also the same. And so now we want to set up what is our differential equations for each of our tanks. So as we did in the first one, in the first video, we showed that the change in volume with respect to time equals the flow going in to the tank minus, so here for tank 1, minus the flow leaving the tank. And as we showed, volume is nothing more than the cross-sectional area times the height. And so we can go ahead and rewrite this as our change in height over time equaling the flow entering tank 1 minus the flow leaving tank 1, all divided by the cross-sectional area. And now we're assessing for how the fluid level in tank 1, how the height of that is going to change with respect to time. And then really it's the same thing for tank 2, which we have the volume. Let's just go ahead and it's the same principle, but here we have the height of tank 2, and let me go ahead and say H1, H2. So that is going to be the flow entering, which is Q12, the flow leaving is Q23. They have the same cross-sectional area. And then tank 3, I'm going to erase this over here. Tank 3 is how height changes with respect to time, and then that is Q23, which is entering. Does that look like a 2-3? Not really. Entering tank 3, and then Q3 is what is leaving, and then this divided by the cross-sectional area. And so these are our differential equations of modeling how much is the height, the fluid level height for each tank 1, 2, and 3 going to be changing with respect to time, which is based upon the right-hand side of each of these equations is the flow in minus the flow out divided by the cross-sectional area for each tank. And so let's go ahead and model what that looks like now in Python and be able to assess it visually. Now starting up the coding in order to simulate our controls and the flow and how everything will change with the fluid level in the tanks. A number of the things are going to be the same as what we did in part A. And so we'll go ahead and take some of the tools that we used. We're going to be using the same tools. We're going to be doing an array of values. We're going to be plotting to see how the fluid level changes over time, and using Solve IVP to solve simultaneous differential equations. The parameters, some of these parameters are the same, some of them are not. The H total, we're not using that. We're not doing a conical tank anymore, so we can get rid of the radiuses. The bottom drain at each point of the tanks are the same. Our cross-sectional area we're saying is, I forgot to write this down in the initial thing, but is 1 meter squared. The initial flow rate coming in is 0.1 meters cubed per second. Gravity is the same, surprise. The fluid level, the initial fluid level at steady state, this we derived from part A, and we're going to look at it over the same course of time here. And so now let's go ahead and go about defining the right hand. Well, we set our right hand equation, which is right here. This is our right hand equation for each of our height levels in the tank, but now we're going to go ahead and code that out in a function. So we're going to define the right hand side of each of our tanks, the equation here. So we always have our independent variable first, which is time in this case. How are things changing with respect to time? And then our dependent variable is a vector, an array of values here. And so we'll go ahead and call that V, because then what we're going to do is we're going to say the height of tank 1, the height of tank 2, and the height of tank 3 are all going to be their own array of values here. And let's change this here. Give that the variable name is the initial steady state of flow coming in, because then we're going to be assessing how does our if our flow rate in is now changed to a 20% increase of the initial flow rate at steady state, what is going to happen over time? So now we need to model how the flow rate is going to be changing. And if we go back to looking at the steady state, well, at steady state, we know that Q, so steady state, at steady state, Q in equals Q out. And so if we do the general term here, as we talked about in the first video, everything, the kinetic energy per unit mass is going to be everything that starts at the top of the tank and then drops down to the bottom of the tank, which is going to be all the potential energy that it consists of, that it holds up here, getting converted into kinetic energy down at the bottom, which means we can then say as, here we go, so Q in equals, so Q out is going to equal the cross-sectional area at the bottom multiplied by the square root of 2GH. And this is going to be the generalized expression. We're going to say that for height in tank 1, 2, and 3. So let's go ahead and model that out now. So we have Q12 equals AH multiplied by 2 times G times H, all to the square root. And then we can copy and paste this 2 more times, and then just change the variable name. So we got Q12, Q23, and Q3. And then the only thing that changes here is height 1, height 2, and height 3. Now what is getting returned, return MP array, we want to return array of values. Now the array of values is again the height is right here, which is how is our fluid changing with respect to well, it's going to be how it's changing with respect to time, and this is how we derived this out. And so if we go here, we showed that how each tank is changing with respect to time. Here is Q in minus Q, what's coming in minus what's coming out of the tank, all divided by the cross-sectional area of the tank. And so we can go ahead and say that for each of these now. This is what we want to kick back out as our array of values from our function here. So Q, what did we say? We said Q in minus Q12, Q in minus Q12 divided by AC. Second function is, my phone just turned on, it heard me say second and thought it was Siri. Me saying Siri. All right, Q23 minus, nope, sorry. Siri just distracted me. Q12 minus Q23.
1 sec.
Divided by AC, the cross-sectional area. And then lastly, Q23 minus Q3 divided by the cross-sectional area. So let's see if it likes that. Great. Okay, so now we're going to move on to using our solve IVP. Solve IVP. And what is it that we're solving? Well, we're solving our right-hand equation over a particular time span. So we're going to say 0 to t end. Here we've got our list of values, which is H naught, H naught, H naught, because we've got 3 different heights, right? The fluid heights in all 3 tanks here. And then we're going to, since we're doing multiple differential equations and trying to plot them out, we're going to use a little bit more of a powerful tool to capture that effectively. And then just as we did in the first video, we want to be able to have a solution kicked out at any particular time that we're interested in. So we're going to say dense output true because we want to know at 2500 seconds what is the fluid height in tank 1, 2, and 3, and so forth. So that this way we can pick any time we want and get a value. Okay, it didn't like that. It said Q I naught is not defined, right? Because I didn't rerun all the things from the beginning. Okay, there we go. Now, another thing is we're going to call this as variable result. That way, if we say, give me at 25 seconds, result is not defined, of course. Keep forgetting to run each time. So now it's giving us our value at 25 seconds in. What are the heights of each tank in tank 1, tank 2, and tank 3? And so this makes sense already right off the bat. We see that tank 1, we would expect tank 1 to be quicker, or not quicker, but higher, because it's the first thing that is receiving flow in. And so if the flow rate is higher in tank 1, or if the flow rate is increased going into tank 1, well, tank 1 is going to be the first thing that elevates, and that's then going to be what increases the flow rate leaving tank 1 to then enter tank 2, and then that's going to then enter into tank 3. And so we should see a lag, we should see a delay, because tank 1 is going to experience it first, tank 2 is going to slowly catch up over time, tank 3 is going to slowly catch up over time, but any immediate changes, tank 1 is going to experience it first, and then so on down the line. So let's go ahead, and the last thing we need to do now is plot, and so we can visually see what is changing over time. So let's go ahead and again steal a little bit from what we previously coded. And we're going to be doing similar plotting here. So we have our time plot. That's where we're assessing our independent variable there, equally spaced over from 0 to whatever our time end is going to be over 100-second increments. But now we don't have 8 because we don't have just one tank. We've got 3 tanks that we're considering, and that is all going to equal our time plot. And then let's go ahead and run that there. It doesn't like too many values to unpack. Okay, there we go. Now let's go ahead and take some of this. We're going to tweak it a little bit. So we're going to make our subplots. Now x, our independent value variable, is tplot. Y1 is now h1. And then we're going to name this one so we can track them. We'll call this one tank 1. And let's copy and paste this out. Oops. And change this to tank 2, height 3, because this is tank 3. And there we go. So, and this is what we expected to see here, because tank 1, it experiences the increase in flow, and we see, sure enough, that it's what begins experiencing the increase in fluid height in the tank before then we should see tank 2 next, and that's indeed what we see. So over time, tank 2 begins to see an increase in the fluid height in it. And then lastly, tank 3, which is what we'd anticipate, takes the longest. It's got the most delayed effect because it's receiving the fluid last down the chain of events here. And then it begins to increase last of all. But because we give it enough time, they're all going to eventually reach a new steady state, and which is what we see. So they're all reaching this steady state here of 7.34 meters cubed per second. And so this here, we're modeling just what happens when you see an increase. If we give an increase of 20% to the initial flow rate going in to 3 tanks, and we anticipated that tank 1 should receive an increase in fluid height first, and then tank 2, and then tank 3, and that is indeed what we see, and they all eventually do reach the new steady state of 7.34 meters cubed per second for the flow rates. Thank you.